Okay. So let us move on to the next application of binary search. So what we want to do now is find what is called the maximum or minimum depending on the case, as we'll see soon why I said depending on the case, in a unimodal array. Okay. So first of all, what is a unimodal array? So a unimodal array is one where the array values either increase and then decrease, or it decrease and then increase. So if the array values increase like this 4, 5, 8, 9, 10, 11, and then starts decreasing 7, 3, 2, 1. So it's like this 4, 5, 8, 9, 10, 11, and then 7, 3, 2, 1. So it's called a concave down unimodal array. Okay. So in a math class you would have seen what's a concave down function, concave up function, and stuff like that. So this is looking like a concave down function, and for such functions there is a maximum where the peak is. Okay. So given a unimodal concave down unimodal array, we should be able to find this maximum, and we want to do that using a binary search approach. Similarly, given a concave up unimodal array where the array values keep reducing, like for example 9, 8, 5, 4, and then increase again 7, 6, 12, 14. So that is a concave up unimodal array. And for such an array, we should be able to find the minimum, and we want to do that using a binary search approach. So that's the kind of problem we want to do. Okay, my cursor is not moving. Okay, 1 second, let me see what's going on. It's because of that recording program. Okay, I think it should be fine. Okay, so alright, so let us try to understand this and the binary search algorithm for this problem using an example along with the pseudo code. Okay, alright, so what we will do is this: start again with left index and right index. So here you are given an array like this 3, 5, 8, 9, 10, 14, 11, 4, 2, 1. So this is an array where the values are increasing and then decreasing. So it's a concave down unimodal array, increasing and then decreasing. So for such an array there should be a maximum, and that's what we want to find. So the maximum could be anywhere in this array. So we start with, so the entire array as a search space. So the left index is 0 and the right index is 9. Okay, so the search space ranges anywhere from the left index to right index. So that's what I say, L equals 0 here, indicating left index, and then R equals n minus 1, that's the right index, initial value. So as you have seen so far in binary search, as we go through the iterations, left index either moves to the right and then right index moves to the left. In any iteration only one of them will move, the other will stay at that place for that iteration. So we'll continue the iterations as long as the left index is less than the right index. The moment the left index is going to be equal to the right index, we will say we have found the maximum. So the invariant is this. The property you want to maintain is the maximum could be anywhere ranging from the left index to the right index. It could be at the left index, it could be at the right index, or it could be anywhere in between. So that's how we define the invariant for So as you keep reducing the search space, as left index and right index keep approaching each other, we do the iterations, and we stop the iterations when the left index becomes equal to the right index. Okay, so we'll do the iterations until left index stays less than the right index. The moment they become the same, and remember how we define the invariant. The maximum could be anywhere ranging from left index to right index. So if once they are the same, that's where the maximum is. So let us do this. So the middle index is always left index plus right index divided by 2 as usual. So now what we'll do is, once we find the middle index, which in this case says left index is 0, right index is 9, middle index is 0 plus 9 over 2. 9 over 2, we have to choose the integer part, so we'll choose 4. So the middle index is 4. So what we need to do is, we need to decide, we know it's a concave down array, but we need to decide where the middle index is, whether the middle index is in the increasing part or in the decreasing part. So that's what we should be able to decide now. So for that, we'll compare the array value at the middle index with the array value at middle index plus 1. Okay, so if the array value at the middle index, say is this point value, less than the array value at middle index plus 1, then we can be sure that we are in the increasing part of the function of the array. On the other hand, if the array value at the middle index is greater than the array value at middle index plus 1, we can be sure that we are in the decreasing portion of the array. So why we need to decide that? Because we need to decide whether to move the left index to the right or the right index to the left. If we happen to be in the increasing part, that is, the array value at the middle index is less than the array value at middle index plus 1. So by the way, we will also assume that all the elements in the array are in the unimodal array are unique. So there's no need to use the equal to sign. So all elements are going to be unique. So the array value at the middle index is less than the array value at middle index plus 1. So that means we want to look for maximum, right? The concave down function. So we can be sure that the maximum cannot be the value at the middle index, because a value at middle index plus 1 is greater than the value at the middle index. So the maximum cannot be at the middle index or even anywhere to the left of the middle index, because we have decided that we are in the increasing portion of the array, and the maximum cannot be the middle index or even anything to the left of the middle index. So we can confidently discard the left search space and move the left index to even to the right of the middle index. We don't even need to set the left index to be equal to the middle index, because we are sure that the value at middle index plus 1, if it is greater than the value at the middle index, the maximum cannot be anywhere at the middle index or even to the left of it. So we can make the left index to be middle index plus 1, because again the invariant is the maximum could be anywhere from left index to right index. So it could be anywhere starting from middle index plus 1 to the right index. That's where the maximum could be. So we could remove or discard the left search space. On the other hand, if the array value at the middle index is greater than the array value at middle index plus 1, then we can be sure that the maximum cannot be at middle index plus 1 or anything further down all the way to the right index, because we are in the decreasing portion of the array. So, and the array value at the middle index is greater than the value at middle index plus 1. So this is the time where we can move the right index to the left, and we can set that to be the middle index value, because again we want to satisfy the invariant that the maximum could be anywhere starting from left index to the right index. Since the value at the middle index is greater than the value at the middle index plus 1, the right index cannot be even middle index plus 1, it can be even moved further to the left all the way to the middle index. So we said the right index equal to the middle index. So this is how we decide which of the two index values, left or right index, to move. So that's the pseudo code. Find the middle index based on the left and right index values if a of m is less than a of m plus 1. So we can draw it out like this and try to make sense of it. So if a of m is less than a of plus 1, we are the increasing portion of the curve, so we can move the left index to middle index plus 1. So that's what I am doing here. Else if a of m is greater than a of m plus 1, then we can move the right index equal to the middle index. Okay. So we reduce the search space as we go through the iterations, and there will be a time where left index will be equal to the right index, and that time we can come out of the loop and return the value at that index, because left index is equal to right index, so we can just use the left index to access the value and return that as the maximum. So let us do the example using this logic. So left index is 0, right index is 9, middle index is 0 plus 9 over 2, which is 4. So the array value at index 4 is 10 compared with the array value at middle index plus 1, which is 5, and the value is 14. 10 is less than 14, so something like this. So that means the maximum cannot be 10 or to the left of 10. So we move the left index to m plus 1 and set that to be 5, and right index stays at 9. Middle index is 5 plus 9 over 2, which is 7. So at 7, which is the middle index plus 1 is 8, the value is 2. 4 is greater than 2. So we are in the decreasing portion. 2 or even further down cannot be the maximum because 4 is greater than 2. So we can move the right index to the left and set that to be the index 7, which is the middle index. So left index equals 5, right index equals 7, which is the middle index value in the previous iteration. So the new middle index is left index plus right index over 2, which is 5 plus 7 over 2, which is 6. So at 6 we have 11, at 6 plus 1, middle index plus 1, index 7, we have 4. Again 11 is greater than 4. So we are in the decreasing portion, and we can move the right index all the way to m, which is 6. So left index equals 5, right index equals 6, middle index is 5 plus 6 over 2, which is 11 over 2, 5.5, but we truncate and take only the integer part, which is 5. Now the function array value at middle index 5 is 14, middle index plus 1 you have 11. So again we are in the decreasing part, so we can move the right index all the way to the middle index. So you see now left index is 5, right index is also 5. So we come out of the loop and return a of 5 is 14, that's the maximum. So as you see, in doing the iterations, the left index was always less than the right index. So the moment they become the same, we can stop the algorithm and say that's where the maximum is. Any questions so far on this problem and the algorithm for that?
So eventually, both indexes, they met up with each other?
Yeah, both index approach each other, and the moment they are the same, that's where the maximum is. Because you see, always we have to maintain, define the invariant and maintain it throughout the algorithm. So that's what we have been doing in each of those applications. And in this application, our invariant means the property that will be always satisfied at the end of each iteration. So the probability you want to satisfy is the maximum could be anywhere starting from left index to the right index. That's what we want to satisfy in each iteration. So you start with the entire array as the search space for the left with left index 0, right index 9, and we based on what we observe, we can discard 1/2 of the search space. So when a of m is less than a of m plus 1, it means you are in the increasing portion and the maximum cannot be at m or less than m. So we move the left index to m plus 1 and then stay with the same right index as it is. So we do that because the maximum could be only in this range from m plus 1 to the right index. Okay. So we still satisfy the property at the end of that iteration that we are somewhere or the maximum is somewhere from the middle index plus 1, which is our new left index, to right index, or in this case from left index to right index, which is the middle index value of that iteration. So either way, we are reducing the search space and making left and right index to approach each other. And how far we can go until the difference between them is less than, is 1 or above. The moment they are the same, that's again satisfying the property that the maximum could be anywhere from left index to right index, which is that particular index itself. Okay. So what I explained to you right now is also the kind of the proof of correctness of this algorithm. Okay. So in the kind of how you justify in general, this algorithm is finding for you the maximum. And see that, as I said, it's you always maintain you define the invariant and choose the left and right index accordingly, and maintain it in each iteration. And that's what we do in this algorithm. Okay, we're using this figure. We can kind of visualize how to discard the search space and maintain that property. Okay, so is that clear?
Yes, sir.
Okay, good. So let us do the time complexity analysis. So I have one more example which you can practice. This is going to be nothing different. Okay, so let us do the time complexity analysis. So what we do here is as a basic operation, comparison. So comparing the value at middle index to the value at middle index plus 1. So we need to do if a of m is less than a of m plus 1. So that's one comparison. Else if a of m is greater than a of m plus 1. So that is another comparison. Okay. So we do two comparisons to decide how to reduce the search space. Now we have a problem of size n in one iteration. In the next iteration, the problem size reduces by half. As you can see, we either discard the left search space or the right search space. So we are solving only one of those sub problems, means we are searching for the maximum within that reduced search space. So we solve only this problem for one half of the whether from left index to middle index or middle index to right index, right? So that's why it's 1 times C of n over 2. We are not solving both the sub problems, we're solving only one of the sub problems. So that's the basic recursion for binary search, plus the time to decide how which one, either to discard the left search space or right search space. So we need to do two comparisons here to decide that. Now 2 is still a constant, so it's theta of 1. So we can use the master theorem and find a, b, d, and C of n is going to be theta of log n. Now remember, I said at the beginning of binary search, if you do if you spend theta of 1 time to decide how to reduce a search space, in the case of binary search, the time complexity is going to be theta of log n. So you don't really have to even do master theorem, but of course if you apply master theorem, you're going to get that as the answer, theta of log n. So that's again a log n time complexity binary search algorithm. Okay. Now the space complexity is going to be theta of 1 because we are not using any additional space that grows with the input size. Of course, use left, right, and middle index as temporary variables, but there will always be 3 such temporary variables even for array of large size. So we say the space complexity is theta of 1. Okay. So you can try this practice problem. So what we did is concave down. Okay. So you can try similarly for a concave up array like this, and in that case you will find the minimum. What's the minimum element? So again we'll define the left and right index in such a way that the minimum is somewhere within that range, it could be either left or right index or somewhere within that range. And you keep going through the iterations and same process, but here we have to decide how we move the left and right index. It could be different for this problem, but very similar to this, similar idea. So if that is my thing. Thought I had it here. I had my drawing tool here. I thought I can draw and explain it. 1 second. So you have an array like this. So the values are decreasing and then increasing. So you want to find this 4, that's the kind of minimum. Okay. So you will start with the left index as 0, right index as the last index, and the middle index is going to be L plus left index plus right index divided by 2. So if we are, I should be able to find my drawing stuff. Okay. All right. So if we are, say, somewhere here, so the middle index is here, and so always we compare with middle index plus 1. So this is your middle index, and the value at middle index plus 1 is somewhere like this. So what we have here is the function value, the array value at the middle index is what? Greater than the array value at middle index plus 1, right? So it's a decreasing part. So the array value at middle index is greater than the array value at middle index plus 1. So where are we? In the decreasing part. So should we move the left index to the right or the right index to the left? We want to find the minimum, right? So since at the middle index, the array value middle index is greater than the array value at m plus 1, the minimum cannot be at the middle index or even further to the left, because those values are greater than the middle index plus 1 value. So we can move the left index to the right, because the minimum cannot be anywhere from the current value of left index all the way up to m. It cannot be anywhere for those index entries. So we can move the left index to the right and set left index to be middle index plus 1. Okay. On the other hand, if it is the other way, if the array value at the middle index is less than the array value at the right at m plus 1, so that is something like this. So we are in the increasing part, and since the array value at middle index is less than the array value at m plus 1, it will be even less than as you go further towards the right index. So as you go towards the right index, the array values only increase. So that means we can move the right index to the left and set the right index to be the middle index. Okay, so that is how you move the search, move the left and right index. So you can see it is different from here. So here, if a of m is less than a of m plus 1, you move the left index to the right. Here we move left index to the right if a of m is greater than a of m plus 1, and similarly the other way for the right index. Okay, so you should be able to do this problem this is a concave up unimodal array. Any question on this?
I have one final question
Uh-huh.
about the pseudocode.
Uh-huh.
Uh,
Yes.
yeah, you didn't, like, it doesn't say at the end there, it doesn't say, like, what instance the code stops.
You see return a of l, so this is where the code stops.
I wasn't looking at that. Yeah,
Yeah.
I just saw the end. Yeah.
Okay. All right. So let me save this.